So we were using the reference manual to understand the meaning of the various keywords we see in the data file. To give you a quick review, we learned that the minimum set of run spec keywords required by Eclipse 100 are these keywords: title, diamonds. You have to have at least one keyword describing the fluid phases. You have to specify the unit convention. You have to specify the start date of the simulation, and you have to specify the well dimensions. Okay? Now, for each and every one of the keywords that you find in the data file that you have, you can refer to the reference manual. You can get information on it, and you have to do that on your own, because if I want to do it keyword by keyword here, it is going to take a number of hours, many hours. So part of the task is on your shoulders. Here I'm going to cover most of it, but only the most important ones. For the less important ones, you have to do it on your own. Now, back to the reference manual. For the keyword diamonds, we click on it and it takes us to page 655 of the reference manual. Here, under the keyword diamonds, we see that it is used in Eclipse 100, Eclipse 300, and it is a run spec section keyword. You can't use it after writing grid or edit or props or regions or all the other parts of your data file. Now, what does this keyword do? It specifies the dimensions of the grid. If you remember, when we worked with the flow viz and saw the result of the simulation of this code, we saw that this reservoir had 10 blocks in the x direction, 3 blocks in the y direction, and 3 blocks in the z direction. And why was that? That was a result of this little code that we've written here. That was what we specified here. If here we had written 130, 30, then the simulated reservoir and what we saw in the flow viz would have 100 matrix blocks in the x direction, 30 matrix blocks in the y direction, and 30 matrix blocks in the z direction, right? So this is a very basic and very important keyword, diamonds, right? Now, after that, now the keywords that specify the fluid phases available are simple and basic. If you click on one of them, for example, oil or gas or water, I'm going to click on oil. I'm going to see here that this keyword can only be used in the run spec section. And this keyword indicates that a run contains an oil phase. The oil keyword should be specified whenever an oil phase exists or could exist. Okay? Now, back to the run spec section codes. Field metric lab. So in Eclipse 100, 300, and in general, you have 3 unit conventions. The unit of the data that you put into your data file can be in metric system, in field system, and in lab system. When you're working to simulate a real-life reservoir, and in most of your simulations you're going to use field units, but there's still other conventions included, which are metric and lab. Here I've told you to convert the field units to metric units because that is a good exercise. But in real life, real engineering life, you are rarely going to use the metric system. Now, when you write this keyword, it indicates that metric units are to be used. Note that this is the default unit conversion. Okay, so if you want to use field units, you have to write field here. Okay, now this tab dims and vel dims, these 2 keywords. I first am gonna explain to you this vel dims, and after that we're gonna go to tab dims. Now, just like before, let us go to reference manual. And guys, working with the reference manual and technical description is very fundamental when it comes to writing a code in Eclipse and working with Eclipse. When you are a reservoir simulation engineer, which is a very common job, you have to work with Eclipse, and when you are working with Eclipse, there is no better source than its reference manual and technical description to get information on the things that you want to do. So if that is your job to become, if your job is a reservoir simulation engineer, you're gonna do this thing that I'm doing for the rest of your life. This is very important. So we are supposed to see the descriptions on this essential keyword, which is vel dims. Now, as the table beneath it indicates, this keyword is only used in the run spec section. Now, in the data file that I've sent you, you see after the keyword itself, there is one line of comment which doesn't count, and after that you see a couple of numbers. Okay, you see 4, 5, 1, 2, and after it you see a slash. What is the meaning of this? Now, after each keyword that can accept input data, you're going to see a couple of numbers. Here the numbers are 4, 5, 1, 2. But what is the meaning of these numbers? If you want to know the meaning of the numbers, you have to go to reference manual. When you do that, this is what it says. It says the data consists of up to 10 items, right? Describing the dimensions of the well data to be used in the run. The data must be terminated by a slash. And you see in the data file that I've sent you that it terminates with a slash. Okay? Here in the reference manual, it says after the Williams keyword we can have 10 data items. Okay? 10 data items. But in the data file that I've sent you, there are only 4 pieces of data. You see? One is 4, one is 5, one is 1, one is 2. You only see 4 pieces of data. So what about the rest? What about the other 6? This question is going to be answered very soon. The reference manual says that the first data that you write after the Williams keyword is the maximum number of wells in the model. Okay? The maximum number of wells in the model. So in the data file that I've sent you, after the Williams keyword, the first data is 4. So it means that the maximum number of wells in the model can be 4. What is the meaning of the second piece of data? You see here, the second piece of data is the maximum number of connections per well, and that is the maximum number of grid blocks connected to any well, right? So if in this model you have a well, production well, injection well, the maximum number of grid blocks that can be connected to it is 5. Okay? And the fourth piece of data, its meaning is the maximum number of group of wells, because in your Eclipse simulation, your data file, you can group various wells. And that comes into play when you have a very big reservoir of many hundreds of wells. Over there, you want to group your wells. But in the simple cases, one group is enough. When you don't have many wells, you can consider all of them to belong to one group. For the moment and for the basic understanding and application of Eclipse, this grouping of the wells is not important. And the fourth field indicates the maximum number of wells per each group of wells. And the fifth one is the maximum number of steps per separator, stuff like that. That is not very important at the moment. Okay? But at the moment we have to consider two important things. What happens first one is this. First one is that for each, if you look at the reference manual, you're going to see for each field you have a default value. Okay? So if in the data file you don't write the data for a specific field. The simulator is going to consider the default value for it. Okay? So Veldems is a keyword that can contain 10 data fields, but here we only included 4 of them. For the other 6 fields, the simulator is going to consider the default value. And here in the reference manual, it explains that what is the default value that is that the simulator is going to consider for the fields that we haven't written the data for. For example, for the 5th field, the default value is 5. For the 6th field, the default value is 10. For the 7th, it is 5. For the 8th, it is 4, and so on. Now, this Veldems keyword is a necessary keyword of the run spec section, but for the simple cases that you are going to work with, it is not very important. You just have to pay attention that the data that you enter in the first field is the maximum number of wells. So if your model has 10 wells, then the maximum number of wells specified here should be bigger than 10. If you have many matrix blocks, you have to increase this number so that the matrix blocks connected to one well doesn't exceed this maximum that you have set here. Okay? That is a very important piece of information that you have to keep in mind. And the more important point is to understand how Eclipse uses the keywords to get the input data, right? After each keyword, from these 2 examples that we saw up to the moment, diamonds and Veldems, what did we understand? We understood that Eclipse does this. You name the proper keyword, and after writing this keyword, Eclipse waits for the input data. The first piece of data, for example, in diamonds. Let me share the data file screen with you. Do you see this?
Yes, sir.
Very well. So after writing the keywords diamonds, the Eclipse waits for 3 pieces of data. The first piece that you write here is going to be associated with the number of blocks in the X direction. The second piece of data that you're going to write here is going to be associated with the number of directions in the number of blocks in the Y direction. And the third piece of data that you're going to write here is going to be associated to the number of blocks in the Z direction. Right? Here for Veldems,
this file, or
yes, I've sent you this file.
okay.
Yeah.
So we have to recognize these things you told us?
Exactly, all of them. And if you don't, you have to go to reference manual. Okay? I've explained all of it.
Yeah.
So, this is the pattern that Eclipse uses to get the input data. Okay? And we're gonna have more explanation on what? Go ahead. Questions?
No, sir.
Very well. Now, the next section of data in Eclipse is the grid section. Okay? What about the grid section? In the grid section, what do you do? In the grid section, you specify the important geometrical properties of the reservoir that you are simulating and some basic rock features. Okay, so you specify some basic geometrical properties of the reservoir that you're simulating, and you also input the rock properties data. What do I mean by that? For example, here in the data file grid section, you have a keyword called dx. The meaning of dx is the length of the matrix blocks in the x direction. dy is the length of the matrix blocks in the y direction. dz is the length of the matrix blocks in the z direction. Perm x is the permeability of the reservoir in the x direction. Perm y is the permeability of the reservoir in the y direction. Perm z is the permeability of the reservoir in the z direction. Poro is porosity for every matrix block in the reservoir that you're simulating. Tops is what it is, the depth of the top layer of the reservoir that you're simulating. Did you listen to me? These pieces of information that I gave you are very important. Now, let us concentrate more on each of these keywords, dx, dy, and dz. These three are going to give you the length, width, and thickness of your reservoir. Okay? Now, in this reservoir that we're simulating, one very important point is when we want to input the data in the grid section, first we have to pay attention to the number of cells that we have defined for the simulation of the reservoir. In the dimension section, here I've decided to have 10 matrix blocks in the x direction, 3 matrix blocks in the y direction, and 3 matrix blocks in the z direction. What does that mean? how many matrix blocks I'm gonna have in overall.
90.
Exactly, 90. If you thank you, Shahyar. In the flow vest simulation that we saw in the previous lecture, you saw that cubicle reservoir that we simulated had 10 blocks in the x direction, 3 blocks in the y direction, 3 blocks in the z direction, and overall in each layer it had 3 layers, and in each layer it had 30 blocks. So overall it had 90 blocks. Okay? Now, in the grid section, when we want to write the data for dx, we are determining the length of each and every one of these 90 matrix blocks in the x direction. Okay? So, we have to input the data for 90 blocks. Right? Now, we have decided, imagine that we have decided to write the length equal to 1000 feet for every block in the x direction. So what do we have to do? We have to write 1000 feet 90 times. Do you agree with me? Guys, this part is super important. Please pay attention. Do you agree with me? If the length of each block in the x direction is 1000 feet, then after this dx keyword, I have to write 1000 feet, which is the length in the x direction, 90 times for each block. Because I have 19 blocks, I have to write 1090 times. Right?
Yes, right.
Good. So, instead of writing 1090 times, Eclipse lets us use this multiplication symbol. Instead of writing 1090 times, I can write 90 times 1000. Yes? I also have decided that the length of each block in the y direction has to be equal to 1000 feet. So I have to write 1000 feet 90 times. So I write 90 times 1000 feet. Also, I decided that the length, the depth, the thickness of blocks in the z direction are 50 feet. So I have to write 50 for dz 90 times. And I can write it in this way. 90 times 50. Okay? Now, here, because I'm converting the units from field convention to metric convention, I have to change this 1000, which is in feet, to meters. How do we convert feet to meters? 1 feet is equal to 0.3048 meters. So 1000 feet is approximately equal to 0.4.8 meters, or approximately 305 meters, 305 meters. So here, when I want to do the conversion to the metric system, 1000 feet becomes 305 meters. 1000 feet becomes 305 meters, and 50 feet becomes 15 meters, right? Now, for permeability in the x direction, y direction, and z direction, it's still the same. I have to define the permeability in the x direction for each of the matrix blocks, right? Now we know that the rock properties that are given to us tells us that the permeability in the x direction is equal to 200 millidarcies for everywhere in the reservoir. So for each one of those 90 matrix blocks, I have to write 200 millidarcies once. So I write 90 times 200 because I have 90 matrix blocks, and the permeability in the x direction for each of them is 200 millidarcies. For perm y and perm z, again the same. But do I have to change this when I want to convert the units from filled to metric? No, exactly, because in the metric system also the unit for permeability is millidarcy. Okay? For porosity, the information is this. In the first layer, the porosity is 30%. This is the thing that the geologists and the ones who work in the rock properties labs tell us. They have gathered the samples, they have done the experiments, and they have given us the data. They are telling us that the porosity in the first layer is 30%, in the second layer is 23%, and in the third layer is 18%. And it is only logical. As we go deeper into the reservoir, the overburden pressure gets higher, and we usually have a smaller percentage of porosity, right?
Right.
Now, in the first layer, we have 30% porosity, and in the first layer, how many blocks do we have? 30 blocks. Okay, so we have 30 blocks with porosity equal to 30%. Then we have 30 blocks with porosity equal to 23% in the second layer. And in the third layer, we have 30 blocks with porosity equal to 18%. Right? So, after the keyword porosity, I write 30 times 0.3, which is the 30% for porosity, then 30 times 0.23, then 30 times 0.18. Okay? Guys, there's 1 minute left from this meeting. Let us have a 5 minute rest. Then I'm gonna send you a new link and we're gonna
So
continue
how long are we going to continue?
10 minutes after we come back. Okay?
Okay, sir.
Thank you very much. Thank you very much.
Thank you.
Situation.
Go ahead.
What will happen if the first layer of the grids have different permeability or porosity?
That is a very, very good question. We have to learn how to number the matrix blocks, which I haven't taught you yet. When we do that, for example, if the first line in the first layer has permeability equal to 300 millidarcies and the next two lines in the first layer have permeabilities equal to 150 millidarcies, then we have to write 10 times 300, then write 20 times 150. I'm going to teach you this in the next lecture. When it comes to zoning, which is the part B of this exercise, you're going to learn everything about this.
Thank you, Ustad.
No problem. So guys, now I have to announce your homework for the next week. You remember that I gave you a data file which included 5 injection wells and 4 production wells, right?
Yes, Ustad.
Very good. In that data file, you're gonna have to convert the units which were in field units to metric units. Okay? And you're gonna have to do that from the top of the data file till the bottom. Okay? If you if you have missed that data file that I'm talking about, I'm gonna send it to you again. Don't worry about that. But the way that you're gonna do that is very much similar to what we've done here. You can look at this data file in which the changes have been made, and you can look at this as an example to learn how to this unit conversion in the data file. That is your homework. Okay? Now, there is another keyword in the section, which is called tops. Okay, in the grid section you have a keyword which is called tops. What does this keyword do? It determines the depth of each block in the simulation that you are doing. Okay, so this reservoir that we are simulating has 3 layers, and we know that the depth of the top layer is 5,000 feet. Okay, so For the 30 blocks that we have in the first layer, the depth is going to be 5,000. For the blocks in the second layer, the depth is going to be equal to what? It is going to be equal to this 5,000 plus the thickness of the first layer. The thickness of the first layer was 50 feet. For the 30 blocks in the second layer, the depth is going to be 5,000 plus 50 feet, which is 5,050 feet, right? So for the first 30 blocks, the depth of the top of the block is 5,000. For the next 30 blocks, look at the screen, the depth of the top of the block is 5,050 feet. What about the blocks in the third layer? The depth of the top of the blocks in this layer is 5,000 feet plus the thickness of the first two layers of the reservoir, which is 2 layers of thickness equal to 50 feet, which is 100 feet. So the depth of the top layer of the depth of the top of the blocks in the third layer is 5,000 plus 100. So it is 5,100 feet, right? So we write 30 times 5,100, right? Now we have to convert these data into metric units. 5,000 feet is equal to 1524 meters. 5,050 is equal to 1539 meters. 5,100 feet is equal to 1554 meters, right? So questions? No problem. So it is enough for today. I'm gonna send you the first data file that we worked on, in which we had 5 injection wells and 4 production wells. You have to convert the data in that from filled units to metric units. That is the exercise for the next week. So, any questions?
No, sir, thank you.
You are welcome. See you next week. Goodbye for now.